All right. Good afternoon, everybody. This is question 47 from the midterm review. This question and the next two of them that I'm doing kind of all go together as like three chapters in a sense. So, but consider this chapter one of three of the intermolecular force, if you will. So in this case, we're looking at four different species, excuse me, of molecules. We're trying to figure out what sorts of intermolecular forces we have present between them. So let's take stock quickly of what sorts of intermolecular forces exist. So we have, for starters, we have London dispersion forces. This may just be dispersion forces. I'm not sure how Dr. Shepard's doing this for you. So this is to say we have, so here's some nucleus here, all right, and we have an electron cloud that surrounds it, right? Now this kind of thinking of the electrons as it being in a cloud, and the cloud really being a probability distribution, is a little different from the quantized discrete sense of things that we have when we think of it in terms of Lewis structures. Like for instance, if you're drawing ammonia, right, that is supposed to be an N. You're quickly rattling off some sort of a tripod structure, and you're putting a lone pair up here, right? Without any second thought. This isn't necessarily the case. I mean, like, we do have a lone pair that's present, and this sort of accounts for it in a good, like, geometric way. And we would see these three hydrogens be like more or less in this configuration. But these electrons we would not expect to be in the same sort of formulaic fixed geometry, tetrahedral geometry, as the nitrogen and the hydrogens are. Right? So the electrons we have to think of as a little bit differently. And it's from that lots of these different forces emerge. Okay, so the dispersion forces are where you just have ripples, like you don't have a perfectly even distribution. We have some electron here that went this way because this one moved this way, then the one behind it moved this way because there's a void that's created, and then the electron rushes in to fill it, right? Like, just different ways to think of it. It means that you may have a shape that looks like this 1 second, all right, and then maybe the next looks like this, all right, and these are relatively minor changes, right? And they differ, I guess, in some of the other ones in that they're not defined in terms of what causes them, but just it's sort of a little of a catch-all category for very weak forces that aren't induced by dipoles or ions or hydrogen bonds or any of the other sorts of things, right? But you could sort of consider them as electron cloud irregularities, and this does create some sort of like there's less electron density here than there is over here, right? So to some tiny degree, one would have to see that as that and that as that. Or there has to be some kind of net positiveness here and net negativeness there, even if it's just transient and disappears as quickly as it comes. So these little irregular things we call dispersion forces. All right, dispersion forces. Whoops. Dispersion forces. Okay, so that's those. All right, so we can have dipoles that exist. These could be permanent or these could be induced. All right, so let's look at an example of one of our molecules here, which does have a permanent one, and that's the ammonia molecule. So when I draw ammonia, I would I'll try and do my best for a real adult 3D one here. Something like that. And we put our electron pair up here, which we understand is not, necessarily here, but we put it here anyway. But this does show us very, very clearly that there does exist some kind of a dipole structure here. We have hydrogens at the bottom. These are going to have some sort of a net positiveness, which is going to gradually increase to net negativeness as we move towards nitrogen. Nitrogen's quite electronegative in comparison with other species. It's capable of hydrogen bonding as well, which means it's exceptionally electronegative. So this is going to have a permanent dipole fixture, right? Meaning the electron concentration, if we sort of consider the whole ammonia molecule like this, you'd expect the electron cloud to look something like this, and then just a tiny amount of it like that. Right, meaning that if there's more ammonia molecules like further back here, this electron cloud is gonna have a very easy time attaching itself to the back there and such like that. And you can see how these consequently, or you know, reinforce each other with each subsequent molecule that you add to it. So that's an example. That's an example of permanent dipoles, right? So we'll put that in as a, you know what? Actually, let's do it a little differently. We'll put dipole, and then we'll just put subcategories after. That's a better way. Okay, so dipole, and now we've seen permanent with respect to the ammonia there. Let's have a look at an induced dipole. Okay, so we could have a molecule of, let's say we have sodium there, which is very much positive, right? And we have these littered about in solutions, right? And this is actually going to be defined as something differently in a second, because this is going to be an ion induction, but this is just to show you sort of an idea of what's happening. If this happens to be passed by a molecule that doesn't necessarily have so much of a dipole, let's use our carbon tet as an example, right? This is a neutral molecule. Chlorine's extremely electronegative, but because we've got chlorine in each direction at even angles, are all 109.5 degrees or such like that from each other, so this is even balance of the electronegativity. But if we have a source of sodium over here, like we could imagine that these were just added into solution just now, this is all of a sudden going to have an overwhelming electron concentration this way, right? All of them to this side because of the positive ions over on this side. So these positive ions induce this irregular distribution of electrons in the carbon tet. So we would call that an ion induction or ion induced dipole. All right. So that's an idea there. Let's get rid of this. Let's find another kind of induction. We can have molecules that do have dipoles in existence. We're going to use the carbon monoxide here. We're sort of like answering this question by going through all of these. As you see, so hopefully you're seeing we're killing two birds with one stone here. So let's put the carbon monoxide atom here. This very much has a permanent dipole over this way. Write it something like that, where you cross with a positive here. So that means that if I do something like this, this has some sort of a distribution like this. All right, that's sort of what you can picture. So then, if this thing goes by a molecule that does not have a dipole in it, so to speak. Let's say we have. What's an example of this? We could use a hydrocarbon to force them away. So I think part of the bottom there was probably cut off by the screen, but this is going to force the electrons in this direction here. The presence of these oxygens moving this way towards the hydrogens. All right, so we would expect more electron concentration on this molecule on that side of it. Okay, so that is induced dipole action. So we can add that to the list here. And we've just about done the whole lot of them. There remains only one extra category, which is really just an extremely severe case of dipole interaction. That's hydrogen bonding. This only happens in a couple different molecules. Nitrogen's one of them. Oxygen's one of them. So if an interaction between, let's say, water and ammonia, for instance. So if we have H2O here, we write O with the two H's, right? Very much a polar structure. Two different lone pairs here, which means massive concentration of electrons on this, like towards the top side here. And we have ammonia. You could show this between water and water, but this gives us an opportunity to show two different structures at once here. But these free lone pair electrons, that's really the key in the hydrogen bond. It can interact extremely strongly with these hydrogens here when they're associated with these atoms. And so it's sort of a twofold reason. A, you have lone pairs present, right? These are what interact with the hydrogens. So they move to the hydrogens. And the second reason is that these hydrogens are exceptionally positive because of how electronegative the central atoms that they're with are. So in a water molecule, this OH bond, I mean really any OH bond, but especially in water, is extremely polar, right? That means there's very, very little electron concentration there and massive amounts of it up here. And that means that when the lone pairs interact with the hydrogens, they can really, really interact with the hydrogens. So the other aspect of this is that the hydrogens are very much polarized by the presence of these other atoms. So that is that's our intermolecular forces in a nutshell. That's a little more theoretical detail than I usually like to put in these videos. But like I said before, it sets us up very much for the questions to come, right? So no polarity in this means we're just looking at dispersion forces. There's not going to be dipoles here. Oxygen and carbon, there is a permanent dipole present. This can induce dipoles in other nonpolar interacting molecules, right? This is also polar, right? This is going to be capable of hydrogen bonding in addition to dipole induction and such. And nitrogen is also nonpolar, similar to the carbon TED over here. And all four of these are going to be capable of dispersion forces because all four species have electrons present. All right, hopefully that's helpful. We'll see you on the next question.